We continue with subtopic 7.2 Chemical Properties of Haloalkanes. At the end of this subtopic, students should be able to explain Sn1 and Sn2 mechanisms, show Sn1 and Sn2 mechanism of a given haloalkane, and compare the relative reactivities of primary, secondary, and tertiary haloalkanes toward hydrolysis or alcoholysis. Now we discuss about mechanism of nucleophilic substitution reaction of haloalkanes. There are two types of mechanism for nucleophilic substitution reaction of haloalkanes. The first type is unimolecular nucleophilic substitution reaction. The symbol is Sn1. And the second type is bimolecular nucleophilic substitution reaction. The symbol is Sn2. Both of the type of mechanism are depending on the structure of the haloalkanes and strength of nucleophile. What is bimolecular nucleophilic substitution? Sn2. Sn2 is a process of bond breaking and bond forming occur simultaneously. As one bond is forming, the other bond is breaking. Sn2 mechanism involves only one step. It is second order reaction, which is the rate is equal to K multiplied with concentration of haloalkane to the power of 1 and multiplied with the concentration of nucleophile to the power of 1. Thus, the rate of reaction is proportional to the concentration of haloalkane and concentration of nucleophile. Consider the following reaction. CH3CH2Br is a primary haloalkane. It's react with sodium hydroxide aqueous under reflux. The nucleophile is OH-. OH- is a strong nucleophile. OH- substitute the halogen atom bromine in the haloalkane to form an alcohol, and the side product is NaBr. According to this chemical equation, we need to choose the most suitable mechanism for the nucleophilic substitution reaction of haloalkane. The chemical reaction involves primary haloalkane, therefore the most suitable mechanism is Sn2 mechanism. Let's learn to write Sn2 mechanism. First, draw the haloalkane reactant in form of 3D structure. Halogen, bromine at right side of the compound, and another 3 bonds are projected to the left. Carbon-bromine bond is a polar bond because bromine is more electronegative than carbon atom. Nucleophile attack the electron-deficient carbon atom, which is carbon bearing the halogen atom, bromine. To minimize the repulsion between haloalkane and nucleophile OH-, the OH- attacks the electron-deficient carbon atom at the site opposite to the halogen atom. At the same time, bond between carbon and bromine break. Both of electrons from the bond move to the bromine atom. The step occurs slowly, and this step is a step to determine the rate of chemical reaction. After nucleophile attack the electron-deficient carbon atom, the transition state produced. Transition states show the process of bond breaking between bromine and carbon and show the bond forming between OH- and carbon. The process occurs simultaneously. When the carbon nucleophile bond begins to form, the carbon-halogen bond becomes weakened, finally broken. The X-, which is Br-, is decreased. Look at the inversion of configuration. Initially, CH3 and another two hydrogen atoms are projected to the left, but in the transition state, all of the group of atoms are at the middle of the transition state. And finally, at the product, all of the group of atoms are projected to the right. As the displacement takes place, the configuration of the carbon atom undergoing substitution invert. It turns inside out the same way that an umbrella is turned inside out when caught in a strong wind. For haloalkanes with the same halogen, reactivity of Sn2 reaction increases in the order of tertiary, secondary, primary to methyl halide, according to the steric effect. Steric effect decreases from tertiary, secondary, primary to methyl halide. The lowest steric effect, the most reactive toward Sn2 mechanism. How about unimolecular nucleophilic substitution, Sn1? What is Sn1? Sn1 is a first-order reaction with the rate law, rate equal to K multiplied with concentration of haloalkane to the power of 1. Therefore, rate of reaction depends only on the concentration of haloalkane. Sn1 mechanism involves two steps, which are formation of the carbocation and nucleophilic attack. Look at this example. Haloalkane react with sodium hydroxide aqueous under reflux to produce alcohol, and the side product is NaBr. The nucleophile is OH-. OH- substitute halogen atom bromine to produce an alcohol. The most suitable mechanism for this chemical reaction is Sn1 mechanism because the chemical reaction involves tertiary haloalkane. Now we write the Sn1 mechanism. Step 1 is formation of carbocation. Tertiary haloalkane is the most reactive toward Sn1 mechanism. It is the example of tertiary haloalkane. CH3, 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 C bromine. Carbon-bromine bond is a polar bond. The bond breaks by heterolytic cleavage. This step occurs slowly, and this step is a step to determine the rate of chemical reaction. After carbon-bromine bond break, tertiary haloalkane produces tertiary carbocation, which is the most stable carbocation, and bromine is released as Br- ion. Step 2 is nucleophilic attack. Nucleophile OH- attack the electron deficient carbon atom in the carbocation. A new bond is formed between nucleophile and the carbon atom. This step is fast. The carbocation is planar and can be attacked equally well from either side, in front and at back. For haloalkanes with the same halogen, reactivity of Sn1 reaction increases in the order methyl halide, primary, secondary to tertiary haloalkane. It is according to the stability of the carbocation. Stability of the carbocation increases from primary to tertiary carbocation. The most stable carbocation, the most reactive toward Sn1 mechanism. Sn1 and Sn2 reaction depends on both the concentration of nucleophile and the identity of nucleophile. A strong nucleophile is one that reacts rapidly in Sn2 reaction, and a weak nucleophile is one that reacts rapidly in Sn1 reaction. Let's look at the sum of the common strong nucleophile and weak nucleophile. Finally, we compare between Sn1 and Sn2 mechanism. Sn1 is unimolecular nucleophilic substitution, while Sn2 is bimolecular nucleophilic substitution. Sn1 is first order reaction according to the rate law, rate equal to K multiplied with concentration of haloalkane to the power of 1, while Sn2 is second order reaction according to the rate law, rate equal to K multiplied with concentration of haloalkane to the power of 1 and multiplied with concentration of nucleophile to the power of 1. Weak nucleophile normally related to the Sn1 mechanism. The example are H2O and ROH, alcohol. And strong nucleophile related to the Sn2 mechanism, which are OH- and RO-. Tertiary haloalkane is the most reactive toward Sn1 mechanism, followed by secondary, primary, and methyl halide, and vice versa for Sn2 mechanism.